The next page in your packet gives you an entire step-by-step rundown of solving a system of 3 equations with 3 variables. I'll briefly talk through the steps, and then we'll use those steps to apply to a problem. But this is here all worked out for your convenience. The first step is to take our given system and to rewrite it in what we call standard form. Standard form is where all the variables are on one side and the constant is on the other of the equation. So we may have to move things around. Here we've got a 3 in the wrong place. Here we've got 3z in the wrong place. And so we need to move some terms, add and subtract from both sides, so that we get the equations, all of them, into standard form. Once we have the equation in standard form, we take two different pairs of the 3 equations. Now, you're taking 2 pairs, so we're going to use one equation twice. That's okay. And you'll see in the example that I am using that second equation twice. But we select a pair of equations, we choose a variable to eliminate. So we'll use that elimination method that we talked about for 2 variable systems here to eliminate one variable. And then we'll repeat with the other pair of equations. Eliminate that same variable. It is extremely important that you're eliminating the same variable in both pairs. The big picture goal is to take this 3 variable system and turn it into a 2 variable system. So you want the same 2 variables left over when you do the elimination. So here in the example, we have the first equation and the second equation, and the second equation and the third equation. So we're taking the first 2 equations, we're eliminating z, and in the second pair, we eliminate z again. So if I were to do this out, I notice that negative 4z plus 2z, I can't eliminate them as is, but if I multiply this second equation by 2, when I add them together, I get 11x plus 4y equals negative 3. And we can do something very similar here, eliminating z, scooting over to give us more room. If I look at the z's here, even though it was really convenient to eliminate z's in the first pair, it's not so convenient here, but we could still do it. Multiply the first equation by negative 3 and the second equation by 2. And we get the same equation here, negative 13x plus y equals 15. Now we have 2 equations, 11x plus 4y equals negative 3, and negative 13x plus y equals 15. Notice they have the exact same variables in there. We'll rewrite them and solve that system. So filling in the details here, I can either use elimination or substitution once I have this 2 variable system. I'm going to try to use elimination here. I tend to like elimination a little bit more than substitution, but that's just me. Okay, if I'm going to eliminate, it says eliminate y, so let's try it. The first equation I'll leave by itself. The second equation we'll multiply by negative 4. And negative 13 times negative 4 will give me 52. 4 y's will cancel, and I add them together. I get 63x equals negative 63. So x equals negative 1. Once I have x equals negative 1, I can plug it back into either of these 2 equations to find y, because I used both of the equations to find x. Now I can plug it into either to find y. 11 times negative 1, y equals negative 3. Negative 11 add 11, we get 4y equals 8, so y equals 2, and that matches. So we have x equals -1 and y equals -2 that we got from that two variable system. Now, once we have two variables, we take those two variables and we substitute them back into any of one of the original three equations. As long as that original equation has the missing variable that we need to find, we can take the two variables that we found, plug them in, and find that third variable. So filling in the details here, 5x minus 2y minus 4z equals 3. And sure enough, we do get z equals -3. Putting it all together, our solution is -1 to -3. And then to check it, we would take this answer and plug it into all three of the original equations and make sure that it checks out. Now let's try it on an example. So here we have our system. The first thing we're going to do is make sure that it's in standard form. So the first equation checks out, x minus 3y plus z equals 2. Second equation is okay, 2x plus 4y minus z equals 10. But the third equation, I've got -2z. My z term is on the wrong side of the equal sign. So I need to add 2z to both sides. And I need to move my x. So I want x's in the front. 3x minus 4y plus 2z equals 8. So we'll add 2z to both sides. I like to label my equations just so that I know what I'm doing. I'm going to label them with letters, and I'm going to call equation C the standard form equation instead of the original equation. We need to choose two pairs of equations. So when I look at these equations, I'll hopefully try to talk you through what it is that I'm seeing with the equations and why I choose what I choose. Now, you can choose any two equations and any variable to eliminate. One choice could be more difficult to complete than another choice. So we want to be wise about our choices. If I look at my x terms, I have 1x, 2x, and 3x. I could pick the first two equations and eliminate x, and I could pick the first and the third equation and eliminate x, and I only need to multiply that first equation by -2 in the first pairing and by -3 in the second pairing. So that's a possibility. Looking at y's, I see that I have a positive 4y and a negative 4y, so B and C chosen together. If I try to eliminate y, that would be really easy, but I have to somehow incorporate A in the second pairing, and -3y plus 4y, I would have to multiply both of those by numbers in order to be able to eliminate, multiplying the first one by 4 and the second one by 3, so that I have 12 and -12y. Looking at z's, plus z minus z, a plus b is going to be really nice because plus z minus z, they'll cancel. If I look at C with the 2z in there, that's actually not too bad because I could multiply B by 2 and add them, and I get -2z plus 2z, and it'll work out. So for my choice, I would pick A and B, and then I would pick B and C and eliminate Z in both. But remember, you have choices, and you can make a different choice and still end up with the same solution. I like to pick choices that require the least amount of work because it also means that there's less likely that I'm going to make a mistake in the calculations. So if we pick A and B together, x minus 3y plus z equals 2, 2x plus 4y minus z equals 10. Because I'm eliminating z, I'll add them. Plus z and minus z will cancel. And I end up with 3x plus y equals 12. Now I'm going to repeat that for b and c. 2x plus 4y minus z equals 10. 3x minus 4y plus 2z equals 8. Now I know it's tempting to just go ahead and add these right now, but if I add them and I eliminate the y, then I have an x term and a z term, and those don't help me together. I need these two equations, these two resulting equations, to have the same variables. So we're not going to add these as is. We want to eliminate z again, the same variable. So I'm going to multiply this first equation by 2 and keep the second equation as it is. And now when I add, the z's will cancel. And we end up with 7x plus 4y equals 28. These are the two equations in my two-variable system that I'm going to solve. So we'll write them down. 3x plus y equals 12. 7x plus 4y equals 28. We can solve this system of equations with either substitution or elimination. So going back to the big picture, we take our three-variable system and reduce it to a two-variable system. Solve the two-variable system, and then we go back and find the variable that we eliminated in the first step. We're going to go back and find z after we find x and y. Since I used elimination in the last example, I'm going to use substitution here. I have a really nice equation, that first one. Y equals negative 3x plus 12. I can subtract 3x from both sides. I solve for y. And then I'm going to take that expression and plug it in for the y in the second equation. Remember, when we're doing these systems, we use one equation, then we use the other equation and solve for one variable. Once we solve for one variable, then we can use any equation to solve for the second variable. But we have to use both equations to solve for one variable. So we'll plug that y back in. 7x plus 4y equals 28, and y is negative 3x plus 12. And we'll distribute that 4, and we end up with x equals 4. Now that we have x equals 4, we can go back and find out what y should be. 3x plus y equals 12. 12 plus y equals 12, so y is going to be 0. And there's our other variable. Notice right now we're only working with our system of two equations to solve those two variables. Now that we have two variables, we're going to take those two variables and find z by going back up into any one of these three equations that has z in it, plugging those values in and solving for z. I'm going to take this first one, x minus 3y plus z equals 2. So we'll plug in our numbers, 4 minus 3 times 0 plus z equals 2. 4 plus z equals 2. So if I subtract 4 from both sides, z is negative 2. So my solution should be 4, 0, negative 2. Let's check. 4 plus 3 times 0 plus negative 2, does that equal 2? 4 plus 0 minus 2 does indeed equal 2. And then in the next equation, 2x plus 4y minus z equals 10. And 8 plus 0 plus 2 does indeed equal 10. And our last equation, negative 4y plus 3x equals negative 2z plus 8. 0 plus 12 Does that equal 4 plus 8? And it does. Since all three equations are true when we plug in our answer, our solution to the system is 4, 0, negative 2. A few notes about solving systems. If, when we're solving this two-equation system, or even when we're trying to eliminate a variable in the first step, if we end up with all of our variables eliminated, then we're going to have a situation of either no solution or infinitely many solutions, very similarly to what we had when we did systems of two variables. If our variables are eliminated, all of them, then we'll either have a true equation, like 0 equals 0, 5 equals 5, or we'll have a false equation, 0 equals 5. If we have a true equation, then we'll have infinitely many solutions, and we'll use the same techniques we did for systems of two equations to come up with a way to generate those solutions. But if we have a false equation like 0 equals 5 or 0 equals something not 0, then that's indicative of a system with no solutions.